Welcome to the 10th and last topic in CP0. In this topic, we'll talk about the set and the map. So these are two important data structures. So here in this topic, we will discuss why we need these structures, what kind of performance they provide, and how to use them in different contexts. We will not talk about how to implement these data structures. So that's the that you should learn in a data structure course. For example, at Purdue, it will be 251. You will learn how to implement this. But I think it's important to first understand what kind of performance they provide and why we need them. That will give more incentive and understanding for learning this data structure. So the reason we need this data structure is in some sense because there are some limitations for vectors. So in this course, we have used the vectors a lot. It's a very powerful data structure. However, it does have limitations in the sense that some operations in vector are very expensive. And here by expensive, we mean that they take time linear in the length of the vector. So when you write a code using these expensive operations, it might be one line of code. You look at it and think that's kind of like a constant operation, but actually it's linear. So this will make some algorithm too slow to solve problem efficiently. So you should think about the complexity of these common operations on a vector. So access one element, push back, insert the element in a certain position, and find the value from the beginning to end, and erase, delete an element. So think about the complexity for each of them. So a hint is that either it's linear or it's constant time. You should think about which one is which. Okay, so I assume that you have thought about the time complexity, and here's the result. The accessing an element is constant time, and the reason is a vector is essentially an array. So in an array, the elements are stored together adjacently. So if we are saying I want to access the case element, so starting counting from 0, then because I know how large each element is, so then I know where the case element will be in this array. So if I'm doing int 4 bytes, then the tens A10 will be from the beginning. I should go 40, 4 times 10. So these calculating where this position is can be done using a few operations. So this is a constant time. Whether we are using this value or assignment, they are all constant time. And pushback and add an element at the end of the array. So this is average case constant time. So because a vector is dynamically sized, so first we allocate an array that are of certain size, and if when we add an element, there is still enough space for that element, then what we do is we simply store the element there and then increment the length of the size of the vector. However, if we are out of space, we use all the element in the array, then we need to allocate a new array, and then we need to copy this old array into this new array. So that one pushback operation will be fairly expensive. However, when we allocate new array, generally we will double its size. So then for the next many pushback operations, the operation will be constant time. So essentially, occasionally we will pay for this linear time copying. And by always doubling the length when we need more space, the turns out that the average cost is constant. So the cost of copying say 1 million 1 million element array into a 2 million element is long, but then for the next 1 million element we don't need any cost. So this 1 million copying can be averaged amortized over this next 1 million operation. Then it's on average constant time. So this is something, if you don't fully understand, that's fine. This is something you should learn in data structures. But pushback itself is fast. Insert is another story. And the time complexity of insert depends on the position. So if the insertion happened at the end or near the end, then that is okay, it's a constant time. But when we insert, we have to shift all the elements in the array that are after the current element back, so that we create the space. We don't want to erase, we don't want to lose any of the element already in the array. We want to add this in there. So this, if we are inserting an element at the beginning, then we have to copy all the current element, move it to the next position, and then we add this element in the beginning. So the cost of that is linear, is the length of the vector. So depending on where we insert, the complexity will be different. But on average, if we assume every position have equal probability, then the average complexity is also linear, basically half of the array length. So that's still linear. And worst case, it's linear time. And similarly, find is average and worst case linear time, because to find an element in a vector using this find operation, which doesn't assume the array is sorted, we have to check every element and compare with this value and see whether that equals or not. So the worst case, we'll compare everything and then find out none of them is equal. The best case is the first one we look at is actually the value. On average, we will expect to look at half of the elements, modulo some assumption, but average and worst case is a linear time. Similarly, erase is a worst and average and worst case linear time, because when we delete an element, we don't want a hole in the array, because then the logic will be wrong when we try to access the element at the particular position. So we have to copy all the elements after the current position, move each of them to the space in front of it. So then depending on where we are erasing, the cost can be linear time. So it's most expensive when we are erasing the first element. So when you use vector, when you use one of these operations, you have to, one of the more expensive operations, you have to realize that's actually linear time complexity. So sometimes we want to do this operation a lot. We want to do find a lot. We want to do insert a lot. So can we improve the complexity of these operations? So that's what the set provides. So a set is a collection containing no duplicate elements. So when you try to add an element to it, if it already have one that equal to the one you are adding, it won't add it. So that's the mathematical concept of a set. It's a collection that contains no duplicate element. But the data structure set, as implemented in STL, so there is a set and there's an unordered set. So set by default is ordered. And if you know Java, or you are going to learn Java, there's a direct mapping. So set corresponds to TreeSet in Java, and unordered set corresponds to HashSet in Java. So they provide very similar functionalities. So a set will support these operations efficiently. So testing for membership, so which can be done using either find or count. So find, it will look for an element and return a iterator pointing to that element if it exists. And count will count how many times it occurs. In a set, each element will occur either once or 0 times. So there's other data structure called multi-set where element can appear multiple times, but we're not not going to use them in this course. Also, adding element using insert method and removing element using erase. These are also efficient, so they are not linear time. And more specifically, in set, the complexity is log n. And in unordered set, the complexity is on average constant time. So the worst case, this could be linear, but that's very, very unlikely to occur. So for all practical purposes, these access are constant time in unordered set. And the implementation is hinted by the name of the Java classes. So set is implemented using what's known as a balanced binary search tree. And this unordered set is used using hash table or HashSet using hashing. So both concepts you should learn in a data structure course. And in set, as opposed to unordered set, there's also elements are ordered, and there's additional support for efficiently finding the first element, the last element, and also, I guess the most important is the order traversal, because in unordered set, I can also find the first and last, but it's just that first and last doesn't have much meaning when there isn't no order. But we can traverse the element in order, so we can find the next bigger one. So for example, you have a set of integers, we can traverse all these elements efficiently. So essentially, given the iterator pointing to one element, finding the next one take only log time. So another similar data structure is a map. So a map can be viewed as a set of ordered pairs. So every element in the set is a pair, two guys, a key and a value. So this is actually literally, I think, implemented in C++ as a pair. So you use the pair class, a key value for map. And in a given map, each key can appear only once. So yeah, we don't allow the two key. There are two keys. Then we don't know which value corresponds to that key. Yeah, so different keys can map to the same value. So for example, one use of map is to count how many times something occurs. So for example, given a string, given strings, we can count how many times a string occurs by mapping a string to an integer, which count how many times it appears. So then certainly different string can have the same value. And a map can also be used to implement a multi-set. So multi-set means that it's a collection of things, but something can appear multiple times, and number of times matters. So using map, we can map the thing to the number of times it occurs. So then that implement a multi-set. So there's actually conceptually, abstractly, there is a relation between array and map. They actually provide fairly similar functionality in some sense. Because the array can be viewed as a map from set of integers to a set of values. So the set of integers are the indices. So if we have an array of 100 elements, then it provides the mapping. 0 will map to some element, 1 will map to some element, 2 will map to some element, and so on and so forth. So when we want to use a map where the set of indices are small integers, we typically just use array because it's faster. It may be require more space, but it's faster. So the trade-off is better. However, if we have a map where the key is not small integer, it could be big integer. So if we have the value of our integer, let's say go from 0 to 10 to the 9, we cannot allocate array that big. So then we can use map. Map can be viewed as an array where only some element exists. So the ones we haven't put in values there, they don't even exist in the map. So we can map a integer to a value, which can be viewed as an array where the indices are sparse. Not all indices are actually used, but they can be very big, so they cannot be implemented using an array. But map can also be used to map other values, a string, or even pair of values. So you can build up complex data types and then use that for either key or value in map. Okay, so next we are going to look at some example problems that illustrate the usage of set and map.